How can a rail, just 16.5 millimeters thick, withstand the crushing force of freight trains weighing up to 30,000 tons, the equivalent of 5,000 African elephants, racing over it at 100 kilometers per hour, day and night, without ever breaking? To achieve such extraordinary mechanical strength, raw iron ore extracted from deep within the earth must undergo an intense transformation, from solid-state direct reduction and electric arc melting to continuous casting, rolling, and a series of rigorous inspections. Join Factron Process as we step behind the scenes of massive heavy industry plants to uncover the entire astonishing process of manufacturing railway rails. The journey of the railway rail began with stone-cut grooves that guided wheels in ancient Greece, before evolving into wooden rails used in European mines. As the age of steam gathered momentum, however, the railway industry reached a major impasse. Cast iron rails were brittle and prone to sudden fracture, while wrought iron rails wore down and deformed too quickly. The turning point came in 1830. Robert L. Stevens' flat-bottom T-rail design, later combined with the Bessemer process for mass-producing steel, ushered in the era of ultra-hard, high-carbon steel rails, creating the vital arteries that would connect the world. Today, the total length of railway track worldwide has surpassed 1.6 million kilometers, enough to circle the Earth nearly 40 times, with heavy industry plants producing more than 12 million tons of rail steel every year. Russia's legendary Trans-Siberian Railway alone stretches approximately 9,332 kilometers across 2 continents, linking Moscow with Vladivostok through 8 time zones, while continuing to withstand some of the harshest weather conditions on the planet. The journey begins at nearly 2,000 mines of all sizes around the world, where approximately 2.6 billion tons of iron ore are extracted each year, the equivalent of nearly 82 tons every second. Across vast open-pit mining complexes carved into spiraling benches that descend hundreds of meters into the earth, crawler-mounted hammer drills bore grids of blast holes up to 50 feet deep into solid ore bodies. ANFO and emulsion explosives are then detonated under carefully controlled conditions, instantly breaking apart more than 1 million tons of ore-bearing rock. But this relentless expansion can come at a heavy cost. In 2020, blasting at Rio Tinto's Jucan Gorge mine destroyed 2 rock shelters, preserving evidence of 46,000 years of Aboriginal history, triggering a parliamentary inquiry and reshaping global mining practices for cultural heritage protection. As soon as the fine dust from the blasts begins to settle, enormous Komatsu hydraulic excavators return to work. Their backhoe buckets scoop up the shattered rock and dump it directly into mining haul trucks powered by engines producing up to 4,000 horsepower. Each vehicle carries hundreds of tons of raw ore per shift, keeping the vast supply chain in constant motion. Leaving the extraction site, raw rocks measuring more than 1 meter across are dumped by mining trucks directly into the feed hopper of the primary crusher. Here, manganese steel jaws driven by hundreds of kilowatts of power exert immense mechanical pressure, crushing the massive rocks down to fragments measuring between 100 and 200 millimeters. This stage releases large quantities of hazardous silica dust into the air, directly threatening workers by damaging their lungs and potentially causing chronic silicosis. Heavy-duty conveyor belts then carry the material through a secondary cone crusher. Once the ore reaches the required size, it is mixed with water and continuously fed into a massive horizontal ball mill, approximately 4 meters in diameter. Inside the rotating drum, thousands of steel balls collide violently with the material, grinding into a liquid slurry containing ultrafine particles smaller than 0.1 millimeters. Finally, a hydrocyclone classification system continuously separates the material. Oversized particles that have not yet reached the required fineness are set back into the grinding chamber, while the uniformly fine slurry moves on to the next processing station. This physical transformation reduces the ore from roughly 1,000 millimeters to less than 1 millimeter, increasing its total surface area tens of thousands of times and liberating the iron oxide crystals from the surrounding silicate rock. The finely ground slurry is pumped through rotating drum magnetic separators and flotation systems to thoroughly separate the magnetite ore from the silicate tailings. The goal is to raise the iron content above 67%, reducing impurity slag during smelting. The concentrate is vacuum dried, mixed with 1% bentonite, and fed into pelletizing discs to form green pellets, measuring 0.35 to 0.63 inches. Qualified pellets are gradually dried, hardened at approximately 2,280 to 2,460 degrees Fahrenheit, and cooled under controlled conditions. They are then charged into a Midrex vertical shaft furnace, where hydrogen and carbon monoxide-rich gas flows upward from below, removing oxygen from the iron oxide without melting the metal. The final product is sponge iron, or DRI, with a metallization rate above 92%. It retains its spherical shape, but becomes porous like a sponge, ready for refining. Alongside the DRI stream, the plant receives steel scrap from old rails, structural beams, vehicle bodies, and machining waste. The current trend is to maximize the use of clean scrap to support a low-carbon circular economy. The process begins at a vast collection yard, where every incoming truck must pass through an automated radiation detection gate. This is a life-or-death safety barrier, shaped by the Cobalt-60 accident in Ciudad Juarez between 1983 and 1984. When an abandoned radiotherapy machine was mistakenly sold to a steel mill. More than 4,000 people were exposed, over 7,300 tons of steel were contaminated, and more than 800 buildings across Mexico and the United States had to be demolished. Electromagnetic cranes then lift the scrap and drop it into a 2,000-ton hydraulic shear, cutting it into pieces smaller than 1 meter. Lightweight sheet scrap is compressed into dense blocks by a baler, allowing the material to be stacked securely, melted evenly, and charged into the electric furnace without causing blockages. The journey now enters its most critical stage, steelmaking inside a massive electric arc furnace, or EAF. The process begins as scrap steel is dumped onto the furnace bottom to form a load-bearing base. Sponge iron, or DRI, together with quicklime and carbon, is then continuously fed through an enclosed conveyor directly into the center of the furnace. 3 graphite electrodes descend and release an intense current of 80,000 amps, generating a plasma arc with a core temperature above 10,800 degrees Fahrenheit, and melting the metal into a liquid bath, heated beyond 2,900 degrees Fahrenheit. Inside the furnace, the added quicklime and dolomite react with oxidized impurities, binding them together to form a thick layer of foamy slag floating on the surface of the molten steel. This slag acts as a protective shield, preventing the liquid metal from absorbing nitrogen and hydrogen from the air, while also retaining heat and removing non-metallic impurities. Finally, the molten steel is poured into a ladle refining furnace, where alloys such as manganese and chromium are added in precise amounts at exactly the right moment. These elements significantly increase the rail's strength and its ability to withstand extreme loads. The qualified molten steel is then sent to a continuous casting system, where it solidifies into large, exceptionally clean blooms. The process begins as the steel flows through an airtight submerged entry nozzle into a tundish, before descending into copper molds cooled by high-pressure circulating water. The outer layer rapidly solidifies into a steel shell, while the core remains molten. A series of rollers continuously withdraws the strand from the mold and guides it through a mist cooling zone, allowing it to solidify gradually from the outside inward. Near the end of the process, the rollers apply gentle pressure to compensate for shrinkage and reduce internal porosity or centerline segregation. Once fully solidified, automated oxy-fuel torches cut the strand into large blooms approximately 13 to 20 feet long. These hot blooms are immediately charged into a walking beam furnace, where they are heated evenly to 2,190 degrees Fahrenheit in preparation for the next stage. Leaving the reheating furnace, the glowing steel blooms race directly into the hot rolling line. First, they pass through a high-pressure water descaling station operating at approximately 3,190 psi, blasting away the dirty iron oxide scale. Traveling along the roller table, each bloom enters a reversing roughing mill. massive alloy steel rolls compress it under thousands of tons of force, dramatically reducing its cross-section while significantly extending its length. With each rolling pass, the rectangular bloom gradually takes on the distinctive profile of a railway rail. Inside the universal rolling mill, horizontal and vertical rolls simultaneously shape the railhead, web, and base, distributing the metal precisely where it is needed. The rail is not formed in a single pass, but travels through multiple rolling stands with progressively smaller gaps. At the end of the line, laser sensors continuously measure the rail's height, width, and profile. The automated control system adjusts the rolls in real time to ensure that the finished rail meets the required dimensions. Leaving the rolling stands, the rails are still glowing red and contain significant internal stresses. Standard rails are placed on cooling beds, where heat is released gradually to reduce warping and cracking. For rails intended for heavy haul freight lines or highly abrasive curves, the railhead then passes through an online heat treatment system. Compressed air jets or air-water mixtures cool only the running surface at a tightly controlled rate. This transforms the hot steel structure into ultrafine perlite, raising the railhead hardness to approximately 350 to 390 HB and greatly improving wear resistance. The cooling rate must not be too rapid. If brittle martensite forms, the railhead may crack under the repeated loads imposed by passing train wheels. After natural cooling, the rails may still develop slight warping due to uneven thermal shrinkage stresses. A roller conveyor immediately carries each rail into a multi-roll straightening machine, which corrects it in both the vertical and horizontal directions. Here, staggered eccentric rollers continuously bend the rail in opposite directions under immense compressive force. This pressure forces the steel fibers to deform just beyond their elastic limit, removing the permanent curvature. The straightening process is controlled with extreme precision by hydraulic servo systems. If the force is too low, the rail will spring back into a curved shape. If it is too high, residual stresses can rise sharply, creating a safety risk during train operation. This near-perfect straightness removes minor surface irregularities, helping prevent vibration and noise as high-speed trains pass over the track. The rail slides onto a cutting table equipped with a massive alloy steel circular saw nearly 6 feet in diameter. A mechanical clamping beam grips the rail firmly as the blade cleanly cuts away the excess material at both ends, trimming it to the ordered length in just 30 seconds. Throughout the operation, a specialized coolant floods the cutting zone to preserve the crystal structure of the rail head. Precision machining follows immediately. A CNC milling machine completely removes burrs, grinds the end faces flat, and lightly bevels the edges, ensuring that both rail ends are perfectly square when joined. Finally, depending on the track design, a multi-spindle drilling machine automatically produces precise bolt holes, or the ends are left undrilled for continuous rail welding. All removed steel is recovered and returned to the electric furnace as raw material for the next production batch. Before leaving the factory, every rail must pass through an automated inspection line, where both its surface and internal metal structure are examined. High-speed cameras and laser sensors scan the entire length to detect scratches, folds, profile deviations, curvature, or waviness along the running surface. At British Steel, 6 cameras can capture more than 4,000 images of each rail, generating over 100,000 inspection images every hour. Ultrasonic probes then scan deep through the railhead, web, and base to detect internal porosity, inclusions, or hidden cracks. Only rails that successfully pass every inspection are marked and cleared for shipment. Before departure, each rail is labeled with a technical batch code for full traceability. A synchronized walking beam hydraulic lifting system raises the rail at multiple points and transfers it sideways to the packaging area without allowing the steel to bend or twist. To maximize space, an automated stacker rotates every other rail by 180 degrees, nesting the heads and bases tightly together in a balanced bundle. An automatic strapping machine then wraps high-strength steel bands around the bundle, tensions them, and twists them securely into place within seconds. To move a 394-foot rail bundle weighing hundreds of tons, an overhead crane uses a lifting beam fitted with 20 to 30 powerful electromagnets. Once energized, they grip the rails firmly while distributing the load evenly. These steel rails may appear completely rigid, but at such extraordinary lengths, they flex almost like a strand of noodles. This allows specialized trains or multi-axle heavy transporters to carry them smoothly around curves and across difficult terrain, ready to become the solid backbone of high-speed railway lines. And so, the journey from iron ore, buried deep within the earth, to finished rails stretching hundreds of meters has finally come to an end, after passing through a long series of rigorous production stages. These seemingly simple steel sections form the foundation of the global railway network, allowing billions of passengers and vast volumes of freight to move safely across cities, countries, and continents every year. But have you ever wondered how the massive trains that run on these rails are built to travel at high speed with such stability?